All right, thank you very much. So I can continue with what we did before. We talked about the number of divisors, and the last example we saw was, or the first example we saw is how I compute the number of divisors of a number that has lots of divisors. But it's still doable. If I wanted to list them, I could do it in a short amount of time, or not such a long amount of time. But suppose I face in a problem numbers that are just too big and I won't be able to write down the actual divisors. Then I just use the formula. Let's see. See, such an example. Suppose I take from my bag and move a bit further, okay? The actual exam, which I have already, and I look at, I hope it's not visible directly there, and I look at a problem involving the number of divisors, and it's of this nature. Which number has more positive divisors? This number or that number has more divisors, meaning, because I remember when I asked a question like this some years ago and someone during the exam, and they said, what do you mean by more? So I said, I look at the number of divisors. Which number has a larger number of divisors? Not larger divisors, but a larger number of divisors. So let me put this back. That's an example of a problem. So I reformulated immediately in terms of this function u. So which number has, let's write it like this, plain English, has more divisors, positive divisors. Positive divisors, okay, I have the statement, positive. That is to say exactly what we compute with our function here. More positive divisors. Let's say, to make it interesting, 30 to the 40 or 40 to the 30. Both these numbers are huge and they have lots of divisors. We should still be able to decide in a short amount of time which has a larger number of divisors. So I rephrase the question like this. Which number is larger? The number of divisors of, not which of the two numbers is larger, 30 to the 40 or 40 to the 30. The number of divisors of 30 to the 40 or the number of divisors of 40 to the 30. Question. Oh, when faced with a problem like this, and if it is about the number of divisors, what we do, or I recommend we do, is to try and apply immediately or as soon as possible the main theorem that we know, which gives us the formula for the number of divisors. Now, in order to apply the theorem, I needed a prime factorization of this. So I need a prime factorization of, say, 30 to the 40. So I start with a prime factorization of 30. I have 30 is 2 times 3 times 5, exactly, I think. 6 and 7. So, I say 30 to the 40, it's this expression to the 40, 2 times 3 times 5 to the 40. So that's 2 to the 40 times 3 to the 40 times 5 to the 40. Thus, the number of divisors, and that's the prime factorization of this large number, is 2 to the 40 times 3 to the 40 times 5 to the 40. Thus, the number of divisors of 30 to the 40 is equal to, we know what the formula is. Add 1 to each exponent and multiply the results. So it's 41 times 41 times 41. Again, if I had the luxury of being at home working with a calculator next to me, computer, I can multiply that. You do it in your head. 65,000 approximately 65,000. But I'm saying, let's try and do something that's elegant if we can. I just leave it like this. I compute the other one, and I see maybe it's visible. If they are close enough, maybe I use a calculator or I do something to compare them. So let's compute this one right here. It is 40. First of all, prime factorization of 40. I hope it's still visible. Yeah. 40 is, let's say, what's the prime factorization? Is 5 times 8. So 2 cubed times 5. Yes, 8 times 5. Then, yeah, you can draw a line so I can see where, okay, up to that point. Is it visible? Okay. Then I compute 40 to the 30, and then the number of divisors of 40 to the 30. So 40 to the 30 is equal to, okay, it's 2 cubed times 5, this being 40, this whole thing to the 30. So I write it again. It's 2 cubed to the 30, so it's 2 to the 90 times 5 to the 30. It's 2 to the 90, I hope I didn't make any mistake, right? It's 5 to the 30, 2 to the 90. So, in this case, number of divisors is, add 1 to each exponent, multiply the results. It's 91 times 31. Now you see I didn't need to multiply them. 91 times 31 is much smaller than 41 times 41 times 41. This 41 beats the 31, and this 41 times 41 is bigger than 91. So it's clear. Just to make it maybe just a little bit more interesting, we arrange one in the exam where they are a bit close, because otherwise it's too. But more importantly, the procedure for us. We have one main theorem that tells us how to compute the number of divisors. We want to use it. In order to use it, we want to write the prime factorization of the number. So even if the number looks like this, 30 to the 40 or 40 to the 30, we don't panic. It's just prime factorization. Find the prime factorization of this. Now let's see if we can adjust this a little bit to make it a bit closer. Which one was bigger? So okay, in any problem we need to give an answer. So answer here. Which was larger? The number of divisors of 30 to the 40 was too large. It's strictly larger than the number of divisors of 40 to the 30. Okay. Let's see another example. Or is it too difficult now? Suppose I just made up this problem. It's not. I don't know, it's still recording or it's a bit dark. Okay, thank you. If I take, instead of 30 to the 40, if I take just 30 to, you said 35, or maybe it's closer, something smaller. Now, suppose I do a more interesting problem, even more interesting than the one on the exam. But the one on the exam, I said which one has a larger number of divisors. A problem like this, even if the numbers are larger, we use a calculator, or we don't use a calculator if you don't need it. It's the same type of problem. But let's make it more interesting. I want to find what is the first time, what exponent I need to put here in order for this to be larger than that, less than 40. Okay, so find the smallest, maybe. I hope it's not too difficult. I don't want to make this. But it's an interesting question because now this was too big. I decreased this 40 in the exponent. I don't change the 30 in here, in the base. That would change completely the problem. It's another problem. It's the number of divisors. I mean, the prime factorization will be different to start with, but just the exponent a little bit. So find the smallest, say positive integer, let's call it d, for which the number of divisors of 30 to the d, it's larger than the number of divisors of 40 to the 30. Now, how do I do that? Okay. I'm going to do it like this. I compute this even if I don't know d. This is an unknown number, but I write it as a function of d. Then I look at this expression. I compute it, which we already did. So this is just, so I don't repeat the same computation, it's computed. And it is equal to 91 times 31. Let me remove everything else so then we can see. Well, that's a more interesting question, perhaps. So I want smallest d. D for which this 30 to the d, it's strictly larger or equal or strictly larger. Let's say the problem was like this, strictly larger than this number that was already computed and was found to be 91 times 31. Now let's see if we can do it without too much computation. How do I proceed? First of all, I want to find, I know what I want. I want to be able to apply our theorem. So I need a prime factorization of this number. Start with the prime factorization of d, and I have, well, not of the base, 30. So I have 30 is equal to 2 times 3 times 5. So 30 to the d is equal to 2 to the d times 3 to the d times 5 to the d. And the number of divisors, 30 to the d, is, we know we add 1 to each exponent, is d plus 1 times d plus 1 times d plus 1. So it's d plus 1 cubed. So now the problem reduces to the following inequality. Want smallest There's no more number theory, so to speak, at this stage. We use this theorem, say, in number theory, to reduce it to this expression. A cubic expression in D, I just solve an inequality. Let's see. Find smallest D, integer D. So 1, the smallest D, for which D plus 1 cubed is larger than 2 times 3 times 91. 91 times 31. Well, this means D plus 1 to be larger than a cubic root. 91 times 31. If I had the luxury of a calculator, I would just use the calculator. But otherwise, 14. You're saying that that's about this number without using a calculator. Are you cheating? Okay.
Checking.
Checking, okay. But don't tell me. You're saying that 14 times 14 times 14 is too small. So what you're saying is basically the following.
D is 14.
The D is 14. So I can do this without a calculator. There's no point to do it without a calculator. But let's see. We do it without a calculator. As follows. This is an increasing function of D. So if I find two consecutive numbers, one for which this is smaller than this and one for which is larger, then it will tell us what the D is. And if we try approximately, as you said, if I take like D to be 9, there will be a 10. But 10 cubed is not good enough. 10 squared is just a little bit bigger than this, but the other factor of 10 is much smaller than 31. So I agree. Try 14, as you said. For D is 14. Well, D is 14. D plus 1 is 15. And is 15 times 15, that's 15 cubed, times 15 bigger or smaller than 91 times 31? You know what I do? If you tell me, I just divide by this. 91 times 31. Elegant word. I want to show what? What you wanted to show? That this is still small. Or this is big enough. Well, this is about half, about 1/2. And 15 over 91. Oh, this is just a bit bigger than 6. I mean, if I force division by 15 in here, it's 6 point something. This is, yeah, probably this is how I do. This is, I force division here. This is 2 point something, because this is 31 and this is 15. And then I'm left with, as I said, what was this? 6 point something, 2 point something, 12 point something is smaller than 15. Aha. So if I divide them in the other order, this divided by that, 31, what's this? 31 times 91 over 15 times 15 times 15. I can write it as, okay, 1 over 15 is outside, and then it's 31 over 50, if I don't want to use a calculator. But of course, I just made up the problem without thinking if this requires a calculator or not. Okay, 31 over 15, 91 over 15. And now what I'm saying is that this number is 2 plus 1 over 15, actually. 2 plus 1 over 15, pretty small. So it's a bit more than 2. This one is 6. 6 times 15 is 90. 6 plus 1 over 15. And now I say elegantly, I take this times this times this, and I see that it's less than 1. Because instead of these 2, I can put those 2, and I have 2 times 6 is 12. As long as this thing is less than 15, divided by 15 is less than 1. And you're right, because when I multiply them, I don't even need to do the multiplication. Maybe we should close the door, if you don't mind. I know we don't have enough air here. But open the window. But I don't want people to distract us in any way. So it's 2 times 6 is 12, plus 6 times 1 over 15, which is 6 over 15. So see, I do it elegant. I don't even need to multiply them or to add them up. 2 times 1 over 15 is 2 over 15. And then plus 1 over 15 times 1 over 15, that's 1 over 225. It's much smaller than 1 over 15, because it's over 15 squared. But even if it was 1 over 15, plus other 2 over 15 is 3 over 15, plus another 6 is 9 over 15. So this whole thing is less than 9 over 15, is less than 1. Plus 12 is less than 13. I still have to divide by a bigger number. So without the calculator, we did. And so for d equals 14 is satisfied. I don't know if it's the smallest, but definitely the number is, say this number is larger. So, what was the conclusion? The conclusion is this divided by that is less than 1, so the number, this d plus 1 cubed, is larger. Right? So we were here. The conclusion was that this 30 to the 14, already, and d is 14, was not 15, was larger than this number that was equal to, I forgot, mu of, was 40 to the 30. And I need to check, but let's not waste time with that. Then 30 to the 13 is less than this number. So then, after checking this, we can conclude that actually actually answer the d is 14. But I can kind of trust you that this is right, because this was close enough. If you put a 13, but you can redo the computation, you can check. All right. So let's get to the next topic. So this was a more, say, sophisticated example, but the important part, not the computational part of it. The important part for us is to use what we know from this, so say, from the number theoretic aspect of the problem. How do I compute the number of divisors? Even if the exponent is not known, I can still write a formula because I use my general formula, or our general formula, for finding the number of divisors. Next.
Stop the video.
Stop?
Yeah, we'll start a new one for the new topic.
Okay, but it's still the same video that we'll upload first, because I have to go with the other two. So if you want, you can stop. I erased it.